Hi, so here's another example on how to use mathematical induction to prove. So we have this expression, our goal is to prove this using mathematical induction. So we are going to go again using the same step that we did in the previous example. So first, we assume that we say let P of n be our expression. So in this case, you have to be careful. We have two variables here. We have a g and n, but our variable of interest is n, right? So n is greater or equal to 0, and n is in the set of natural number, right? So we are going to emphasize on n in this case. So for the base case, let's just jump into the base case. For the base case, when n equal to 0, so our summation, the summation from of g equal to 0 up to 0 of negative 1 over 2 of 0 equal to of g. So let's call g, this is equal to negative 1 over 2, 0, which is nothing else is 1, right? So and the right side is 2 to the 0 plus 1 plus a negative 1 to the 0 over 3 times 2 to the 0. So this is going to be 2, because 2 to the 0 is just 1 plus 2 basically. So this is going to be 2 to the 0 times 2 to the 1 plus this is going to be 1 over this is going to give you 1, so this is 3, and this is going to give you, again, this part is going to give you 1, so this is going to be 2 plus 1 over 3, which is 3 over 3 equal to 1. So we can see that the left side and the right side are equal, therefore P of 0 is true, right? Now for the inductive hypothesis, hypothesis, we assume that P of n is true. That said, we assume that the summation from g equal to 0 up to n, negative 1 over 2 of g equal to 2 to the n plus 1 plus minus 1 to the n over 3 times 2 to the n. So we assume this to be true, and our goals, so this is the inductive hypothesis. Now for the inductive step, for the inductive step, I'm just going to abbreviate here. So for the inductive step, or you can just fully write it, inductive step, we assume P of n true, show that P of n plus 1 is true. That said, we must show that for all n in the set of natural number n greater or equal to 0, the summation of g equal to 0 up to now n plus 1, right? N plus 1 of negative 1 half of g equal to, so everywhere that I have n in P of n are replaced by n plus 1, equal to n plus 2 to the n plus 2. So this is 2 to the n plus 2 plus -1 to the n plus 2 divided by 3 times 2 to the n plus 2, right? So this is what we have to show. So we have to show that this is true, right? So basically we need to go from the from this side, from the left side, and get up to the right side. And how do you get this expression? So basically what I did, I just went into this expression, I replace whatever I have, and I replace n by n plus 1. So here I replace n by n plus 1, here by n plus 1. So that gave me this expression. So I get n plus 1 here. Because this was n plus 1, it become n plus 1 plus 1, it gave you n plus 2. And here we have, this is n plus 1. So this is n plus 1, right? Because initially it was n. Then down here, this is going to be n plus 1 also. So this is n plus 1. So we have that, right? Now let us try to prove this expression. So in order to prove that, we are going to go from this side. So let me just rewrite it here. So for the inductive step, we must show that the summation of g equal to 0 up to n plus 1 of -1 over 2g equal to the summation of g equal to 0 up to n of -1 over 2 g. Now I missed one step here. So basically, so first, this is what we need to show. I'm going to consider this part and try to get to this. So basically, this is the first part that I consider. Let me just extend this so you can see, visualize it better. So this equal to because again you consider this part, you want to get to this, right? So if we go back here, this expression equal to, I'm just going to extend it. This is -1 half to the 0 plus -1 half to the second to the first plus up to plus -1 half to the n plus -1 half to the n plus 1, right? So because before we get up to n, we went through n plus before we get up to n plus 1, we go through n, right? So that's the n plus 1 there. And this is what, this is like the initial summation is the Pn. So basically this is we can replace this by the summation of g equal to 0 up to n of -1 half of g, right? Then plus we have 1 over 2. This is n plus 1, right? Now based on the inductive hypothesis, we assume this to be true, right? And this was equal to what we can have here is we just replace by the expression that we had for the Pn. So this is our Pn, right? And that was assumed to be true. So we can replace that by 2 to the n plus 1 plus -1 to the n over 3 times 2 to the n, then plus we have whatever we have left here. So I can extend this, I can break this down this way. So this is going to be -1 half n plus 1, right? So this is by inductive step, by inductive hypothesis, this inductive hypothesis, because we replace this expression, we replace this expression by this, right? So this because of the inductive hypothesis. Now from that expression, what we get is we can just extend it. So we have this equal to just a simple math now. So this is 2. What I can do is, because you have 2 to the n plus 1, then plus -1 to the n, then down we have 3 times 2 to the n, then plus -1, you have n plus 1. Here we have 2 to the n plus 1. So what I'm going to do is I'm going to try to multiply the bottom part by 2 and also the top part by 2, because I want to get n plus 1 right here. So what I do is I multiply the top part of this section by 2 and the bottom part by 2 also. So this gives me 2 times 2 to the n plus 1 plus 2 times negative 1 to the n. And then because I multiply that, this is going to be 3 times 2 to the n plus 1, right? And then plus here I multiply the bottom part by 3 and the top part by 3, so I get 3 times negative 1 to the n plus 1. Here I have 3 times 2 to the n plus 1. The reason why I'm doing that is because I try to have the common denominator here, right? That's why I'm trying to do that. I'm doing that. So from that expression, I can just, because we have the common denominator, we can just extend it. So this gives us this expression. So from there, I think it becomes very easy to compute. So from there, we get yeah. So we have this. So from that expression, we have there's something that is missing here. I don't want to spend the time working on that because I already did it somewhere. I just want to copy it basically. So so from here we get this expression, which is whatever you have there. So I can extend this because we have the common denominator here. I can just extend that. This will give me I just put the bottom part, so this is going to be 3 times 2 n plus 1. Then I just copy whatever I have at the top. So this is 2 to the n plus 2 negative 2 times 1, and we have n plus 1 plus 3 times negative 1 to the n plus 1 here. So this will give you 2 to the n plus 2, right? This part. This and this is going to be plus. Then we have negative 1 to the n plus 1. Then the bottom part we have 3 times 2 to the n plus 1. And this is what we was trying to prove, right? We got this. So again, we can just type right here, using mathematical induction, we can conclude that this expression is true. So when you get up to this, you can just write that using by the principle by the principle of whatever principle of mathematical induction, this expression is true, right? So that again was another example on how to use mathematical induction to prove it. And somewhere here you have to be very careful. We extend it this way. So basically from this expression to this, we multiply this part, we multiply all this part by 2, and multiply this part by 2. Multiply this part by 3, we multiply this by 3. It doesn't change. That's why we get this, right? And because it had a common expression here, we can just extend it this way. So this is going to be 2 n plus 1 plus 1. It's just going to be 2 to the, so because this gives you 2 to the n plus 1 plus 1, which is n to the second, right? So that's why we get this. And if you check this expression, this one and this is what we have here, right? And you can just extend that. It gave you, you subtract this, it gave you this expression, and we conclude our proof. So that was another example of the principle of mathematical induction.